Mhm.
Yeah. Uh, Hello, everyone. Welcome to this week's edition of the Data-Driven Learning and Control Seminar series. This is Nishant, and I'm happy to welcome you again. Yes. And today's speaker is Dr. Majid Zamani, and he's a professor at the computer science department. He's a professor at University of Colorado Boulder, and he's with the computer science department. And his talk today is going to be about a correct by construction paradigm for designing autonomous systems. And before we get into the talk, a little bio about Dr. Zamani. And uh, he's currently with UC Boulder. And before that, he was an assistant professor at the TU Munich. And that's where he led the hybrid control systems laboratory. And he did his PhD, and he also got an MA in maths back in University of California, LA. And before that, he was at Sharif University and Isfahan University in Iran. And he has received the George Axel B. Outstanding Paper Award from the IEEE Control System Society in 2023 and the NSF Career Award in 2022 and the European Research Council Concept Grant, Proof of Concept Grant, and Starting Grant in 2018 and 2023, respectively. And his research spans verification and control of cyber-physical systems, secure by construction synthesis, information-based control, and compositional analysis of synthesis of interconnected systems. And without further ado, I pass on the mic to Dr. Zaman.
Yeah, thanks for the nice introduction. And you can hear me, right?
Yep, I can hear you.
Okay, so the talk today is about a correct by construction paradigm for designing autonomous systems. I will explain later what do I mean by correct by construction. So, I mean, as we all know, autonomous systems are on the rise and they're becoming more and more ubiquitous. And of course, this is due to advances in computation, communication, and memory. So, but on the other hand, these systems are actually exhibiting very complex dynamics, and that's due to the tight interaction of the physics and the cyber components in these systems, right? So nowadays, software is actually in charge of controlling many physical variables in these systems. And that's, exhibit very complex behavior. So, and on the other hand, they're also becoming more and more autonomous, right? So, and due to that, they also need to, they need to go through rigorous safety verification because many of these systems are safety critical and they're becoming autonomous. The ensuring safety of the systems are also very important. So let's see what's happening now as a practice. So unfortunately, the design and analysis of these systems are still predominantly developed through heuristic approaches, right? Like trying to take union of existing science, which has been developed in two different community, computer science and system theory, right? System theory for the physical part of the system, and then CS methods and computer science method, namely formal methods for the cyber part of these systems. But due to the tight interaction between the cyber and physics in such systems, we actually need to develop new methods and algorithms, which are more efficient and more formal even. So, and since these systems today has been deployed using ad hoc and heuristic approaches, this can actually lead to some catastrophic events, right? Because again, these systems are safety critical and life critical. So let's see what is the current practice in industry for deploying autonomous systems. So it's mainly based on testing, right? So what is the pros of testing? Of course, testing is great. It's very efficient in identifying straightforward cases, right? And that's what the many self-driving car company already doing. They're actually deploying cars in let's say, in Vegas or in San Francisco and other places, Arizona. So what is the drawback and the main cons of testing of autonomous systems? So of course they can be costly I mean, for example, there is this self-driving car company in China, and in order to, ensure safety while they are doing testing, so they actually allocated one dedicated lane just for self-driving car. So that means human-driven car cannot be even in that lane. So this can be very costly, right? We need to go and change the infrastructure dramatically to be able to deploy this self-driving car. And they can be potentially dangerous because testing cannot find, cannot cover all corner cases, which might happen in reality. The example you can see in the right-hand side picture, it's a Uber car crash happened in 2018 in Arizona, right? And a pedestrian got killed in this car crash. So let's see, if you want to do, if you want to rely on testing autonomous systems, so let's look at these simple statistic. So currently let's look at the statistics in the US. So far we have one fatal crash per every 100 million miles of travel, right? This is the statistics in the US. So let's say we would like to come up with the same confidence, of course, at a rate of 3 to 10 times longer than this mishap rate. So let's see how much testing we have to do. So if we want to achieve similar confidence as human driver, of course, we want to be even better, right? So this requires approximately 1 billion miles of testing to reach similar confidence as human drivers in the US. So this is actually equivalent to making 25 round trips on every road, paved road in the whole world. So, and while we are doing that, going 25 round trips, every paved road in the whole world, we can only allow for 10 critical mishaps occurring in this trip. Then we reach similar confidence as human driver in the US. So, but that's not the end of the story, right? We need to restart the process with every software update, meaning that the confidence we gain with a given and designated, let's say, control software. So now in the moment we actually do some changes or some updates over this control software, let's say while we are doing these 25 round trips, you cannot rely on the previous confidence you have accumulated. It doesn't carry over. So you might actually need to do the test again from scratch. So, okay, with all these things, I want to say brute force testing is not practical, right? It is useful. Still, we need to, do the testing, but it's not the only solution. And we need to do more than that, right? So, and this is the main focus of my talk. So I want to provide a method which is systematic, algorithmic, and at the same time, it provides formal guarantee over the control software that we have synthesized. We have mathematical guarantee that control software works correctly, and you don't need to do the testing anymore, right? Of course, given the assumptions that we consider. So what I'm going to do, I'm going to look at the core of autonomous systems. If you look at the core of them, so they all include what we call embedded control software, right? You have the physical system, which is this, usually described, in system theory, we usually model them using differential inclusion or difference inclusion, right? And then, of course, the states of the systems are observed using sensors. The sensor measurement goes inside this embedded controller, and the embedded controller provides signals to the actuators, right, which are in charge of controlling the car, a steering wheel, or the acceleration. So, but also keep in mind that the control objective for autonomous systems are also very complex. It's not by any means similar to classical objective we used to face. Like classical objective, I mean stability tracking. Nowadays in self-driving car, you have very complex specifications or requirements like respecting traffic rules, respect the speed limit, respect traffic signal, avoid collision, right? Stay in your lane unless it's blocked, right? This type of property are actually very close to what has been told, like it's been investigated in computer science community, they call temporal logic specification, right? And for example, an example of temporal logic specification is called linear temporal logic properties, right? So what is the main design goal for us? I would like to synthesize the control software in an algorithmic fashion, such that when I apply the control software in closed loop to my system, the closed loop formally satisfies the given temporal logic specifications. So that means while I design the controller, I also have the proof of correctness of the controller. So that means I do not need to go later on do the testing to see if the closed loop works correctly. I already have the correctness guarantee comes with the control, right? I mean, sounds very interesting, right? But what is the challenge? I mean, the challenge is the dynamics is very complex. I have a differential inclusion or difference inclusion, and the property of interest are also very complex. These are also, temporal logic specification. They have discrete parts, they have temporal operator, they have logical operators, and the whole thing is very heterogeneous and hybrid, right? And that's the main challenge here in designing these control software. So here is one way of designing control software for autonomous systems. It's called symbolic methods. So let me tell you how this symbolic method works. So you're given your physics, which described by this continuous dynamics. So what we do is we come up with a discrete representation of this continuous dynamics. When I say discrete representation, it's a finite state machine. I come up with a finite state machine that describes the behavior of my continuous dynamics up to some granularity, right? But the good news is now I have a discrete object. So of course I can compose this discrete object with other discrete representation of my hardware and software, which also, part of my embedded control software loop. And now I can have a unified discrete environment that models my overall system. So now I have some property of interest, some specification or requirement of interest, let's say avoid collision, respecting a speed limit. So those properties can be represented using linear temporal logic formula. Now what I can do is I can use game on graph, systematic approach over this finite object to actually systematically generate another discrete object, which we call it discrete controller, that satisfies the requirements of interest, but only on the top part, which everything is discrete, right? But this part is, I have formal guarantee. I know that I can systematically I can push a button, this discrete controller gets synthesized, and I do know if I apply this discrete object over this system will 100% guarantee satisfy the property of interest. Of course, I cannot apply these to my original continuous system. So the last step is I refine this discrete controller to a hybrid one. And also I should mention all these steps comes with 100% formal correctness guarantee. So when I come to this hybrid controller, I do know this hybrid controller, if it applies to my original continuous dynamic, this closed loop in the bottom satisfies the same specification or requirement of interest as I did in the top layer, right? And that's how I get the formal guarantee. So I know this controller is correct. When I apply to my continuous dynamic, the closed loop satisfy high-level given temporal logic requirements. So now you might ask, how do you come up with this discrete representation of a continuous dynamics, right? I mean, a naive and easy approach is just put a grid on your state set. Each of those grid cells represent one discrete state in your discrete domain. And then what you do, you compute over approximation of the reachable set when you start from this cell under one also discrete input value after one sampling time. Let's say this is an over approximation of my reachable set when I start from this cell under discrete input action U after tau second, right? I end up here. So what I do, I will take the intersection of this over approximation with other cells of the grid, and I non-deterministically put transition to all of them. So that means if I start from this symbolic state or discrete state, non-deterministically, I can go to 6 other states, right? And that's how I, discretize my continuous dynamic. Now I have a finite state machine, right? Of course, I have to repeat this for all the cells, and I have to do this for all discrete input values, right? You might say this can be very complex, and you are correct. This can be tough. But I also tell you how we can actually use some parallelization technique to speed up this process. So we in fact have a tool which is publicly available, open source, is called SCOTS. Actually, this tool is becoming a predominant tool in hybrid systems community. In fact, other tools that colleagues are developing in the context of formal synthesis, they usually benchmark against SCOTS and the result of SCOTS. So this tool, what does it do? You put as an input your model dynamic, which is a differential equation, discretization parameter of input and state, and it generates the finite abstraction of the system. Not only that, for classes of property, for example, for safety, for reachability, for reach and stay while avoid, or reach while avoid, for this type of property, it also generates you the controller. By the way, these are all systematic, meaning that you just push a button, it gives you the controller, right? So, and then you might ask, can I use the SCOTS for other complex property? The answer is yes, because 2 major algorithm has been already implemented, minimal and maximal fixed point. So you can actually use combination of these 2 fixed point to actually extend the synthesis, controller synthesis, to larger class of specifications. I don't go into details. If you're interested, I can take that question after the talk. So later on, we said, okay, we need to use parallelization, right? There is a lot of compute units in my computer, and we should be able to utilize all of them in our advantage. So we came up with a different tool called p-phases, which is an acceleration ecosystem for symbolic control. It actually leverages all compute platform in your system, CPU, GPU, hardware accelerator, FPGA even, and it actually parallelized the construction of finite abstraction, or that symbolic system, the discrete representation. It also parallelized the synthesis of the controller. So, and we were able to actually get very interesting result using p-phases. So the next question was, can we apply in a realistic system? So we have this test bed in our lab. So we have these Amazon robots, which are 1/18 scale vehicle robot. They are called AWS Deep Racer. And this is the field we have in our lab. We have a bunch of projectors on top, which are able to project obstacles and different regions in the field. So now, what is the dynamic of the deep racer? This is a dynamic we were able to come up with, identify. And this is the length or the geometry of the fields, right? The x and y coordinate, and theta, and the velocity of the deep racer, right? So now what we did, okay, we build a finite abstraction for this continuous space dynamic. Let's see how many discrete state does it have. Around 6 millions. How many transitions? Remember, from each state, with non-deterministically, you can go to other states, right? So it has over 800 million transitions. So numbers are a lot, large, right? So let's see how long did it take. Actually, to build the abstraction, it took 0.04 seconds to build this finite representation of continuous dynamics. And the synthesis of the controller, it took 0.19 seconds. So these are impressive, right? Given the size of the number of transitions, these are impressive results by just leveraging parallelization technique, right? So let me show you a video, what we are trying to do now. So, by the way, we realize, okay, I told my student, this is very good. Computation is cheap. Can we have a dynamic environment, and rather than having a static environment, and synthesize a controller which for that static environment. So let's make the obstacle dynamic. But then the robot doesn't know nothing about the dynamic of the obstacle, nothing. What robot can do is just, he can every 100 milliseconds can look at the environment, and because the synthesis of the controller is cheap, by the way, the abstraction you only design, you construct one time, because the abstraction doesn't change. The vehicle, if you put it on the different corner, it has the same dynamic, right? The only thing you need to resynthesize from scratch is the controller, right? So we said, okay, are we able to resynthesize the controller on the fly every time it detects the place of the obstacle has been moved, and see if the robot is able to actually go to the target region? And this is the experiments. So initially the robot had no idea there is an obstacle, and then Maddie comes and bring an obstacle, but the robot is able to on the fly come up with a new policy to go back to the target region. So the calculation, by the way, we are not, I just need to also emphasize here, we are generating not only the plan, also low-level controller, everything is encoding. This is not only generating plan, even low-level controller are getting resynthesized here. We just wanted to show the power of, this algorithm being systematic. It can get regenerated on its own, and it's quite fast. Can we achieve this? So that's how we are trying to show this, that it's able, one is able to actually resynthesize the controller. So now the question many of you might ask is, because I am discretizing the space, so you might say, look, you're going to suffer from curse of dimensionality, right? The size of the finite state machine will grow exponentially with the number of state variable. And this is exactly true. So how can we alleviate that? There are many ways. So we can break the curse. How? Two ways, which you use both. You can use hierarchy and compositionality. What do I mean by hierarchy? So rather than designing a controller on your high fidelity system, try to build a low fidelity model out of your high fidelity, and then build the finite representation of the low fidelity model, right? So that's what we do. We go from the original high fidelity continuous dynamic to a low fidelity dynamic. By the way, I should emphasize, in any of these arrows, we quantify the error we suffer. Otherwise, we lose formal correctness, right? We have to quantify the error in all these steps. So, and then in the next step, I'm just going to build the finite representation of the low fidelity dynamic. That's about being hierarchy. The other one is compositionality. What does it mean? So rather than building the finite representation of the whole system, what I will do, I will break down the system and write it as composition of a smaller component, right? Let's say I have a 100-dimensional system. I can look at it as composition of 100 scalar component, right? So now, rather than building a finite representation of a system which is 100-dimensional, what I will do, I will just build the abstraction of a scalar component, hundreds of them, and then compose those finite abstractions together to come up with the finite representation of the overall interconnected system. Again, I should emphasize all these steps comes with formal guarantee. So of course, now I had the finite representation, and I can prove that finite representation all the way top is in fact a finite representation of my original dynamic all the way in the bottom. And now I can do the synthesis of controller. I can design a controller purely in the discrete domain and refine it all the way back to the original concrete interconnected system. And all this arrow comes with formal guarantee, because that's what we are trying to achieve, right? It's called correct by construction. We need to have formal guarantee in all these steps. So, I mean, you might say how this compositional construction of low fidelity abstraction works. The idea is actually inspired from a small gain and dissipativity theory from control theory, right? So what we do is we build low fidelity abstraction of each. So let's say my original system is an interconnection of n component. What I will do, I will build low fidelity model of each component. Let's call it sigma I hat. And then we are able to show under some small gain type or dissipativity type condition, when I take the interconnection of low fidelity representation of components, this whole interconnection of low fidelity models is in fact a good replacement of your original interconnected system. When I say a good replacement means I can show for every behavior in the here, you have a behavior here that you're actually epsilon close, and we can quantify epsilon, right? So every behavior in the original system gets mimicked by a behavior in the low fidelity case, and we can quantify their mismatch as well. So we can do the same thing rather than now building low fidelity model. I mean, when I say low fidelity model, what do I mean? Here is an ODE. This is also an ODE, but lower dimensional ODE, right? So, but now what I can do, I can also build finite abstraction or finite representation of the low fidelity dynamic also in a compositional manner, meaning that if I have a larger scale interconnected system, rather than building the finite representation of this interconnected system in one shot monolithically, what I can do is I can actually build finite description or representation of each component separately and then mix them together. And that's what we are advocating here. And actually, we are able to break the curse of dimensionality by doing this divide and conquer strategy, right? Compositionality approach. This is an example. We were able to, by the way, here we don't do any compositionality. What we do, we don't build a low fidelity model. We try to build the abstraction of the overall interconnected system by leveraging the compositionality scheme I explained. We have a BMW model car, number of state variables 7, and the idea is to come up with a controller that avoid collision in a formal way. Look, we were not asked to come up with a plan. We are asked to come up with a plan and the low-level controller all together. I am actually designing a closed loop feedback controller for this complex dynamic by pushing a click in my computer. So it gives me both in one shot. It's just one controller, right? So we build a finite abstraction. We actually use different hardware architecture, try to speed up the construction of the controller. And these are the time you can see, right? I mean, you might say this is a lot of hours it took to design a controller. The answer is right. But what is important is we are able to design low level together with the plan in one shot as one controller, and we have formal guarantee over the correctness of the controller. And the other thing I want to emphasize is you actually do not need to design those online. You can actually have a library of this controller offline. We can call it motion primitives. You can design these motion primitives offline. And in real time online, you can actually call these motion primitives depending on the scenario your car is being driven. Okay, so far it was about discretizing the space, computing a finite state representation of the continuous dynamics. You might say, yes, compositionality was nice, hierarchical approach was nice, but still, still one might suffer even to build a finite abstraction of even in the component level, right? That also can be challenging. So, I mean, okay, let's go through now abstraction-free method. No need to discretize your space set. You can use barrier certificate, right? I mean, many of you are aware of barrier certificate. For those who don't know what I'm talking about, here is what a barrier certificate is. Assume I'm given a system for now, assume it's a dynamical system, no control input involved, is discrete time. So xi plus is equal to f of xi comma w. W is the disturbance in the system, right? So suppose there is a function b whose domain is the state set of the system, codomain is real number, such that it satisfies this tree inequality. For any state inside the initial set, which depicted by this green region, the value of barrier is less than or equal to 0. For any state inside the red region, by the way, the red region is the unsafe region, the value of the barrier is positive. And for any state inside the state set, for any value of the disturbance, the value of barrier is decreasing along the dynamic of the system, right? So now if I can find a function b satisfying these three inequalities, what does it mean? That means if your system starts anywhere inside the green region, it never goes inside the red region. You have formal guarantee, right? Existence of the function b is your proof of safety, that the system does not go inside the red region. This was in the context of verification, meaning that I wanted to verify if the system starting from green goes inside red. And to answer that question, it boils down to search for a function b. What if I want to design a controller that when I start inside green, it navigates the system and doesn't allow the system go inside the red? Okay, that notion is called control barrier function, right? So now I add control input to my dynamic. So now suppose again there exists a function b, its domain is a state set, codomain real numbers, such that the first two conditions same as before. Inside the green region, which is the initial set, value of barrier less than or equal to 0. Inside unsafe, value of barrier is positive. The only difference is the last condition. Look at this quantifier. It says for any state inside a state set X, there should exist input U, no matter what the value of disturbance is, the value of barrier along the dynamic is decreasing, right? So this is called control barrier function. If I'm able to actually search for a function b satisfying this tree inequality, I actually know how to design a controller k that ensures safety of the system with the help of b. So great, you might say, oh, this is amazing, right? I can just search for a function that verifies the safety of the system or gives me a controller that ensures safety of the system. There is no free lunch. Also, searching for the barrier can be complex itself, right? I mean, I don't know how many of you have used some of the square programming tool to search for Lyapunov function, right? The same thing. Here I'm searching for a function b, right? Or there are other methods like counterexample guided inductive synthesis, they call it SEGIS, that they use usually, satisfiability modulo theory, like SAT solvers, SMT solvers, to search for those functions. They also do not scale well. Like search for this function boils down to, those either SEGIS or optimization problems, and they can also be challenging, right? So now the question is, can we do something here as well? I mean, the answer is yes. The same divide and conquer strategy I explained in the context of building finite state representation or building low fidelity model, similar argument, you can use it here. If I have a large scale interconnected system composed of n components, so now my task is to search for a control barrier certificate for this overall system. But this overall system can have thousands of state variables or millions of state variables, right? And the search for this function can be very complex. So what I will do is I will actually look at this large scale system as interconnection of components. Rather than searching for a function for the overall system, I actually search for some sort of certificates in the level of subsystem only, independently of other subsystems. So I can have n certificates, and then I find a way of composing those certificates. And under some compositionality condition, again inspired by a small grain and dissipativity, we can prove composition of those barrier, in fact, is a barrier certificate for the overall interconnected system. You see, now you break down the search for a gigantic function for the overall system to search for a smaller function in the level of subsystems independently, and then you combine them. And that we show it's in fact a barrier certificate for the overall interconnected system. Okay, so far everything I have explained assume we do have closed form mathematical model of the system. This map F is known. The question is, what if the map F is unknown? You have a black box model of your system. And you're working for a company, they're not going to give you the model, but they only give you a black box. You can interact with the black box, you can provide input, get output, and that's the only information you have. The question is, can we synthesize barrier or even control barrier, the controller, purely based on data without knowing the model of the system? The answer is yes. That's what we have done in a body of work. So what we do here, we generate input-output data from the black box model of the system. We initialize the system, we put bunch of IID sample inside the state set, and we simulate the system starting from those data points. We let the system evolve for 1 unit of time, and we look at the output. So I have capital N input-output data. So now, and I am asked, can I use those data directly to generate a barrier certificate? The answer is yes. We can actually resort to, so the search for a barrier, you can write an optimization problem. Its output is the barrier. But since we don't have the model, I cannot directly solve that optimization. So what I will do, I actually compile a scenario convex problem or a scenario optimization problem from that original optimization problem whose output would have been barrier. So now I solve the scenario optimization based on those n input-output data, and that gives me a function. But still, I cannot claim that function is a true barrier. Why? Because I search for a function only finitely many data points. I cannot claim that function satisfies all the conditions of the barrier for unseen data, right? It is correct for seen data, but it doesn't mean it's correct for unseen data. And that's where we impose some conditions. And as you can imagine, in that condition, I need to know some property of my model. Namely, we need to assume the map F is Lipschitz continuous. And we need to know the Lipschitz constant as well. Based on that, we write a condition, and if the condition is true, based on the barrier that we search for finitely many data points, if that barrier satisfies this extra condition, then we can claim the barrier is actually correct. It satisfies all those conditions of barrier, even for unseen data. So we extend to also control barrier, how to design a controller directly from data. From n input-output data, we can actually generate a controller without any identification. That's what we are promising here. No model identification. It's called direct method. Go from data directly to analysis. Verify if it's safe or not. Go from data directly to the controller. Give me the controller based on data, to no need for identification. So in another recent effort, we actually, so far I talked about safety, systems are safety critical, safety very important. I mean, barrier was ensuring safety of system, right? System trajectory do not enter unsafe region. But then we realized that, what about security property? What about privacy property, right? So I do all this effort. I can claim that my system is safe, but still my system might leak some secret information, right? So for some classes of security property, namely opacity. So if you're interested, after the talk, we can go into details of what do I mean by opacity. But what we are trying to do here is, am I able to systematically design a controller which is not only safe, ensures safety of closed loop, it is also secure. And that's why we call secure by construction. Secure in the sense that the closed loop does not reveal secret information of the system to an outside intruder. Can we also claim that? And the answer is yes, we can actually combine security and privacy property with the safety property. We have a bunch of requirements. Safety is one of them. Security is the other one. And the question is, can I design a controller that enforces both of them? And lastly, we have been interested in notion of assured autonomy transfer. So let me explain what do I mean by that. So in all this work I explained, you design a controller or you verify safety of the system. We spend all this time to design a controller that ensures safety, right? But now there might be some wear and tear in my system. The system gets aged, or I did all these things on on this AWS deep racer, which is an old version, and now all of a sudden I buy a new version, right? Can I immediately put the controller from old version to new version and assume it works? Not necessarily, right? The weight of the robot might be different. The geometry of the robot might be different. So the question is there an efficient way of transferring proof or the synthesized controller from the source domain? Source domain is the domain that I spend all my time to design a controller or verify the property of interest, to the target domain. Target domain is a new domain. It's a new robot, right? Is it possible? Or new environment, right? You have a drone flying in the sunny sky in Boulder. You collect all these measurements. You design a controller, but then you want to deploy it inside a tornado. Is it even possible? Can you find an efficient way by only collecting few amount of data in the target domain? Because it's tornado, you cannot collect a lot of data. You have to collect few amounts of data and immediately you need to transfer the controller, right? Something that keeps the system safe in the new environment. Is it possible? And that's the question we are trying to answer in autonomy transfer. Can I transfer the proof efficiently? Can I transfer the controller efficiently? And we have done some work in that direction as well. For example, if I have a barrier certificate designed for the source system, can I come up with a barrier in the target domain efficiently with low amount of data? Or even in the context of controller, if I do have a controller in the source, can I come up with a controller in the target domain, which also ensures safety of the target system? And that brings me to the end of my talk. This is an acknowledgement to my existing PhD and postdoc and my previous PhD and postdoc and also funding agency. And thank you for all of you listening to my talk.
Thank you, Dr. Zamani, for the wonderful talk. Now we have time for some questions. I'll just ask the questions that we have so far. And, could you give more intuition on how you about the compositionality, like how you break each components? Let's say if there are hundreds, you gave an example where there were like 100 states, 100 components of the state, and you were breaking them into individual scalar components and working on them and then bringing it back to the entire system. So could you give an intuition on how the interaction between these state components is being taken into account when you bring them back?
Yes. I mean, I should also mention that in those body of work, like here, because I also have compositionality in the first part of the talk, right? But I guess this question applies to both. So look, the starting point, we assume the system given to me is already in this form, right? It's already given as interconnection of components. But you might say, no, I give you a big system. You yourself look at it as interconnection of subsystem, right? I mean, I give you an example. X1 plus is equal to f of x1 comma x2. X2 plus is equal to f2 of x2 comma x1, right? So I have a monolithic system, has two state variable, x1 and x2. Dynamic of x1 depends on x2, dynamic of x2 depends on x1, right? And that's how I look at it as interconnection. In this case, I have two subsystems. So, and they are actually coupled, right? Because inside the dynamic that gives me x1, x2 is involved and vice versa. So, but then you might say there are many ways of coming with this interconnected system, right? Like which one to pick? As I said, here we assume the starting point is this. But the problem one might face depending on different ways of interconnection scheme. Because there is this interconnection map M, right? So different way of breaking the system to different components will actually gives you different M as well. Agree? So there are two ways of compositionality. One was based on a small gain, one was based on dissipativity. For example, in the dissipativity, we are able to show that if this interconnection map M has some nice property, actually our compositionality is scale-free. Scale-free meaning that no matter how many components you have, the compositionality condition is always true, right? It's independent of the number of subsystems. But of course, that particular structure of M depends on a very particular way of breaking out the system to the composition of subsystems. And the other thing that might affect, depending on how I break down the system to interconnection of subsystem is, I told you here, you have to come up with a bunch of certificates in the level of subsystem, right? So there are some conditions involved for those local certificate as well, right? So, and depending on how I break down, some of those I might not be able to actually come up with the local certificates in the level of subsystems as well, depending on how this interconnection or this breaking down the monolithic system to bunch of subsystem is. So that's a very interesting question. In fact, this is a question which hasn't been even investigated yet. What is the best? I wouldn't say best. How come I can decompose a monolithic or interconnected system to the bunch of subsystems that I do know it's going to help me with the construction of a local certificate, and it's also going to help me with the satisfaction of the compositionality condition? That's that's an open question on itself as well. I hope that answered the question.
Yep. I think that's a wonderful answer. And the next question is, it's going back to the motivation where like the vehicles were trying to, let's say, stop at the signal or like change lanes only if there was no other car, and all of these multiple tasks. So what if, like, in order to do the testing, we may not be able to quantify what a task is. Suddenly a pedestrian could just walk into the lane and you would want to avoid that. Uh, and this, although this is like just avoiding an obstacle, but like there might be other situations which you might, as a researcher, might not think of, and that could just pop up in the real world. How should one proceed if they also want to look at uh, these unknown or like this things that could just happen when it comes to like satisfying the when it comes to the controller part?
Okay, that's a very good question. So I think I look at this question in several ways. So in my talk, I always use the word formal, right? And I might even misuse it, right? Used it a lot. But it's important to use that. And you might say, why? People who do testing, so one aspect which I did not mention here. I mean, I can talk about here. So remember here, I said I designed a discrete controller in the discrete domain such that it satisfies some property of interest. Here I said temporal logic specification, right? This is actually very important because these properties, for example, linear temporal logic formula, these are very close to human language and they have formal syntax and semantics. That's the very first thing one needs to take care. The requirement of interest needs to be also expressed in a formal way. Because if I'm a designer, you are the customer, you ask me something in a plain English, but I might have different interpretation of what you're asking me to achieve. Actually, we might already lose formality in the very first step when you are outlining the property of interest in an English text and you're asking me to design a controller to achieve that. So the very first step is requirements of interest themselves has to be formal. But at the same time, it has to be general enough to capture what customer has in mind. It needs to be close to English language. And that's the good thing about the temporal logic specification, which has been developed in computer science community. They give you this rich logic that you can actually formally describe them. And they are very close to English. In fact, there are already some tool that you write English. It gives you a, grammar to write your English, and it generates the, linear temporal logic formula for what you write in English. So that's the very first thing, right? So requirements of interest in my work has to be themselves formal in order to guarantee my controller is formal as well, right? So this is now for the case of being able to represent property of interest in a formal way. But I think the question was asking, what if we have not considered some scenarios that might happen in reality, but it might happen, so how the controller is going to react? So, I mean, of course, everything I explained in this work, I assume requirement of interest is given. Meaning that there is an obstacle, I know where the obstacle is, right? And my job is to avoid hitting that obstacle by designing my controller, right? But then you might say, but some obstacles are dynamic, we don't know. So, one way is actually, remember here, you say a pedestrian, right? Maddie can be a pedestrian. The car is trying to go to the target, and all of a sudden, Maddie comes into the road. And the car has to stop. Here, robot didn't know in advance that Maddie is going to jump in. But you might say, how come the robot was able still to navigate? Because that's what I saw in the first part of the talk. Systematic design of controller. You want to rely on the computer. You want the computer does the heavy work for you. You want to push a button and computer just systematically regenerate the controller on the fly. So if something is algorithmic, computer, if it's fast, can actually regenerate the controller on the fly based on the new environment that the car is facing, is able actually to come up with a new plan. And based on that, is able to actually navigate. And of course, depending on how fast the pedestrian jumps, how fast your car is going, it might be the case that when I apply my systematic controller synthesis, it says the domain of the controller is empty. That means I cannot find a controller given this situation, right? So all hope lost? No. Actually, you can always have this type of scenario in mind, and you can design a shield for your system. What is the role of shield? Shield is a backup plan, contingency plan. In case I cannot find a controller in real time, and that's also limit how fast your car can drive. Because you can always rely on the shield that ensures safety of the system. You always switch to the shield. This is the bigger safety controller, which observe all the action the other controller is sending to the system. If the domain of the controller is empty, we switch to the shield, and shield is always guaranteed to ensure safety. For example, it might be the case, in this case, you have to brake hard because the domain of the controller to navigate the car was empty. The best safe action here is just stop the car. And actually, this is also what many self-driving car companies already doing. In a very complex scenario, actually the car just gets a stop, do nothing.
Thank you for the answer. And there is one comment and followed by a question. Like the comment is, I mean, of course, they're appreciating the talk. And the comment exactly is you demonstrated how robot, that is the deep racer, can rapidly synthesize new controllers. And it reminded them of switching systems where ensuring stability can be quite challenging. And the question is, have you considered synthesizing stable switching controllers? And if so, how do you address the stability guarantees? This is from Professor Basant.
So the first part was a comment, right? Was not a question, and that this is related to stability of switch system. If the question is about, because when we have a switch system, ensuring the stability of the overall switch system can be challenging, even if each mode is stable. If I switch between them, I might get like unstable behavior from the overall switch system, right? I need to be careful. How do I do the switching between the modes? I need to have some condition over the switching signal itself to actually get some useful behavior out of the overall switch system. So we actually have done some work for switch system as well. Like you want to design a controller for switch system, let's say achieving practical stability. You might say, why practical stability? Because I can actually write a linear temporal logic formula for practical stability. Because practical stability says reach some region around the equilibrium point and stay there forever, right? That's a reach and stay problem. So the way we are able to actually handle switch system, we have extra constraint over the switching signal, namely dual time condition, right? And actually, because now when I build a finite representation of my dynamic, it's actually very easy for me to add this extra logic that the switching signal, because I can incorporate memory, right? To keep track of the sojourn time. And that's a good thing with the symbolic techniques, because memory is just extra, a discrete variable I need to add to keep track of the memory of the how many times I have a state in that mode. And that's how we are able to actually ensure for the switch system for stability or safety, we keep track of the sojourn time in each mode, and then we change the switching signal to ensure the overall safety of the system or stability even.
Thank you for the answer. Um, like, these are the questions that we have so far, and I think I have one last question. So I'm looking at this from like a reinforcement learning perspective, where like at the end you had a data-based analysis, and having access to the simulator, you are able to generate some trajectories and uh, do this decomposition and do all the certificates. Like, what if one did not have access to a simulator, and what if, and in the case where they just have access to data, as in like some trajectories that was uh, generated prior, and they did not have control over what sort of trajectories could be generated with the system.
Okay, this is a very interesting question, because remember in my data collection, I needed IID sample. But then one might say, but I give you one trajectory, but it's a long trajectory, right? So even if I start collecting data from one trajectory, I do not have this IID assumption anymore. So, I mean, the only work we have done in this direction, which I can. So remember, in my data-driven part, I called it direct data-driven, meaning that we went from data to controller. We went from data to proof. So actually, I can come up with a proof. I can build a proof based on data. You might say, what is the proof? Is the barrier. Barrier is the proof, right? I can build the barrier based on data. So this was direct. And there I needed this IID assumption over the data point. I did not identify any model. But then if I have one trajectory from the system and assume it's lengthy enough, and maybe it's, I also need to assume it's persistently exciting enough, right? These are the assumptions for identification. So I can actually, under some appropriate assumption, even if the dynamic is polynomial type, I can identify a model of the system. And I use that identified model to do everything I did here, right? So, and yeah, that's the only, I mean, I'm sure there are many works are actually being done in control community, which are called indirect data-driven. They try to identify a model using a single trajectory, and then they use that model to, design a controller for safety or stability or other property of interest. I mean, regarding reinforcement learning, we are also doing some work on RL, but I would also categorize reinforcement learning as direct. I mean, you can also have indirect. You can have model-free reinforcement learning, right? You collect data, and then from data, you can actually generate a policy. The only problem with the reinforcement learning is you don't have formal guarantee over the policy you get from the RL. Of course, you have to do the verification at the end again, formal verification. You need to verify if the synthesized policy from RL is actually correct, ensure safety of your original system.
Yeah, definitely. Like I asked that question because these days this offline reinforcement learning is being targeted by a lot of people where there are like safety critical systems and you may not be able to generate these trajectories and you just have these observations. That's why I had that question. But yeah, definitely like we can uh, learn from that if the trajectories are
I mean,
interesting
one
enough.
thing you can always do is in the offline setting, you can use those off data point that is already given to you
Hmm.
to come up with a very rudimentary safe controller. When I say rudimentary, the domain of the controller is very tiny. You can come up with a controller, but it only allows for your system to evolve in a very tiny region. So now you at least in that case, you guarantee that, okay, I am safe, but my robot is evolving in a very tiny region, neighborhood. Now you switch on to the online setting. Now you start exploring and expand the domain of the safety. And now you can add,
Yep.
you add to the domain of the safety as the robot is now collecting more and more data. I think I've seen a lot of work in that direction as well.
Yep. Yep. Definitely. Yeah. Uh, Thank you for your presentation and your wonderful answers, Dr. Zamani.
Yeah,
With
thank you for
this,
having me.
yeah, it's a pleasure. And with this, I think we'll end the talk uh, again. Hello, everyone. Thank you for attending the talk, and we'll see you next in 2 weeks. Next week is Thanksgiving, so we're not going to have any presentations. And yeah, thank you, Dr. Zamani again.
Yeah,
See you.
thank you.
See you
Bye.
soon. Yeah. Bye.